Right, so moving on, seeing as last time we did a bunch of stuff that fixed up the stack because we did JSR and RTS which had to operate on the stack, I feel like this time I might as well implement the stack operations here. Transfer stack pointer to X, transfer X to the stack pointer, push the accumulator onto the stack, so on and so forth. So maybe we could get maybe all of these implemented. So to start with, I'll crack on with the same way I've done this before. I will make a file to put these unit tests in, and we'll make a bunch of unit tests that can test this, then we'll implement the stack operations. So let me just make the file first. So stack operations test, this is just a copy of a previous file. So this is stack operations tests. Let's just stick with, just keep one of these tests as a template. Okay, so let's just go through them in order then. Transfer stack pointer to the X register. This will copies the current contents of the stack register into the X register, sets the 0 negative flags as appropriate. So let's just do that, because I think there's only going to be one test for that. Yeah. So that's absolutely fine. Let's just keep our reset the way we've got it working before. We need an instruction, TSX, and it's just implied. So this just basically takes the current stack pointer and transfers it to the X register. So I think what I'll do is I'll set the X register to be some garbage. Let's just set it to 0. I mean, it's probably already 0, but let's just make sure. And is that all we need to do here? I think that is actually it. We need to get the cycles right, which is 2. Because essentially what we're expecting then is that the stack pointer is the CPU X register is actually the CPU stack pointer. That's it. Oh, we need to test the flags as well. So let's make sure. So that really depends on what the stack pointer is. So let's actually initialize the stack pointer to a certain value. Let's initialize it to FF. Or I need to initialize it to something that isn't going to affect any of the flags at the moment. In fact, I really need to initialize this whole thing. Let's set the, now I can actually set the processor status. Let's just initialize the processor status to all 1s basically. We'll set the X register to 0. We're going to set the stack pointer to something that will not affect, something that's not 0, but will also not affect the negative flag. Let's just set the stack pointer to 1. That seems fine. So at the end of this, we're expecting the X register to be 1. We are expecting the, I think we're calling them flags now. We are expecting the 0 flag. We're expecting that to be false because it's not 0. And we're expecting the negative flag to be false because it's not negative. And just to make sure, yeah, we've actually set those. We can actually set those explicitly up here. Just to the opposite of what they should be. This is kind of what we did in some of the other tests. We're just kind of fudging the CPU into a state where we know that at the end of it, things have to have changed. So that, in theory, should be a good test for that one. And I want another version of that that will set the negative flag, setting flags, let's call it that. And in this one, we'll initialize these to false, and we'll put a value on, oh, trans can transfer a 0 stack pointer to the X register. Let's just call it that. We'll keep these the same, initialize these to true, and we're going to set the stack pointer to 0, and when we do that we are just expecting that the X register is 0 and that the 0 flag is true and the negative flag is false. So I think that's a good test. And then we want one more, a negative. So again, this is similar. We want something that's got negative going to turn up as true. Just something that sets the negative flag. So that's the negative bit there, bit 7. 1, 2, 3, 4, 5, 6, 7. So in theory, what this does then is the X register comes out at that. The 0 flag is false because it's not 0, and the negative flag is true. And that looks right to me, I think. So we just need to add this. Add this TSX opcode, which is BA, and then this should compile, and we got 3 failing tests. There we go. So that doesn't work because we haven't written it. TSX can transfer a stack pointer to the X register, can transfer a 0, and can transfer a negative to the X register. So I think I might implement these as I go now. So let's maybe do that. Transfer the stack pointer to the X register, and it affects these flags. Because now I've got those tests, it shouldn't be too hard. So here we go. There's only one addressing mode. So I've written 3 tests, but I only have to write 1 function. We want to take the stack pointer and we want to put it in the X register. There we go, done. I mean, we can actually put that in and see what we get. I think it'll still fail because we haven't consumed any cycles for that. It's going to take 2 cycles. Is that the thing that's going to fail? Yeah, I think that's the... Does it say? Yeah, we haven't actually set the registers as well. Let's just see if we consume the correct number of cycles, because I think it's 1 to read the instruction and 1 to set the pointer. That should fail in a different way, maybe. Yeah, so we didn't set the value of the flags, and I think we've got a function that can do this. What's it called? Load register set status. There it is. Except this really actually sets the 0 and negative flag. Are they the only ones that we set from a low register? Well, let's just call that, because that's really what we want to do. And call load register set status for the X register. And I think this might make this test pass. There we go. Cool. So I can now transfer the stack pointer to the X register. So let's push on. Now this is the opposite. Transfer the X to the stack pointer. So again, similar thing. This doesn't affect any processor flags, and it's just 1 addressing mode, 2 cycles. So let's put in a test for that. So this is TXS. Can transfer, TXS can transfer X register to the stack pointer. Right, so we don't care about the flags on, do we care about the flags? We just care that they didn't change. We can easily test that now. Anyway, transfer X to the stack pointer. So let's put ff into x. Let's set the stack pointer to 0, hex 0. Let's just set the stack pointer to 0. TXS expects 2 cycles. We're going to execute, expect the number of cycles. We just expect that the stack pointer becomes ff. That's all we expect. We don't test the flags, but we do want to know that the processor status didn't change. So we can do that with this now, because we can just test the processor status as a whole byte. It's a CPU copy, isn't it? Right, TXS. And that doesn't compile because we haven't defined it. And this one is 9A. So again, that should compile and not work. And that's right, we only need that one test for this one. And now we can implement that one as well. So this one should be quite easy to implement. This one copies the current X register into the stack register, so it's the opposite of that one. And I'm going to assume it consumes a cycle, and it doesn't load register, doesn't set the status of any registers because it's doing nothing. There's another good pass. These next ones, what have we got? Push the accumulator onto the stack. Pushes a copy of the accumulator onto the stack. Takes 3 cycles. So this one might be a little bit harder, but it shouldn't be too difficult. Let's give it a go. So I'm going to copy this test. And this is PHA can push a register onto the stack. Cool. So we put something. Let's put something in the A register. Let's put 42 in there. I like putting 42 in there. Let's not set the stack pointer anywhere. PHA expects 3 cycles. So what do we expect at the end of this? What we care about is that the accumulator value, so this 42 value, we can look at the A register value. We care that this A register value is now, is now on the stack. So we need to get the stack pointer as an address, but that will be the stack pointer at the current address, and that will be moved on since we actually pushed that on. Actually, I think it will be at +1, and we expect the processor status not to have changed. So I think that's the right test. So again, we just need to define this one. It is 48. So define that. That should be a failing test, and then we can go and implement it. So we need the A register, and we need to, I think we just need a push byte onto stack. I think we just need a function that does that. Maybe it'll take in the cycles, and it probably needs the memory as well because the stack is in memory. Yeah, I think that's what we need. We need a function that can do that. Have we got anything like that? We've got pop word from stack. We've got push program counter to stack. I think we want a so we're going to push a byte onto the stack. Here's the value, and here's the memory. Let's take a copy of that. Okay, whatever it's going to do, it's going to consume a cycle doing it. We know that. We need to take the stack pointer, turn it into an address, and we are going to set the memory at that point to the value. and then we decrement the stack pointer to move on to the next part of memory. And it actually, in theory, this push program counter to stack, yeah, it could actually use this push button to stack twice. That would be another way of doing it. That might be a better way of doing it actually, because we would then have the stack pointer like incremented in bytes, and it might wrap differently than the way I'm doing it here, rather than this right word thing. I'll leave it as it is for now, but that's something worth considering. Oh, I've made it differently. Put the value in the middle. That might be it. It's not. So what did we get? Instruction 0 not handled. Oh, did I get the wrong number of cycles to do this? Expected cycles is 3 for push accumulator. And did we execute the wrong number? Oh, yeah, that didn't work. Let's go again. We definitely... Let's go in. What did we get? Right, instruction 48. It's going to push the 42 value onto the stack. Let me just take that out of there. Yep. So that's like, we have to promote the stack pointer to its like full 16-bit address. Don't know if that's gonna optimize that out. It might be that I just got the test wrong, but at least we'll know that in a minute. 1FF, that seems right. We're going to push that value into 1FF. We're going to decrement that down to FE, consumer cycle. And then, oh, we got 1 left over. Oh, so there's our problem maybe. That we're not consuming enough cycles to do this. We did 1 for the instruction. We did 1 to push the byte onto the stack. 1 to push the byte onto the stack. And there's another cycle needs to be consumed in there. Where would that other cycle really come from? Why is it 3? It's just 3. It just is. So, I don't know, we've just got to consume another cycle here. 1 to read the instruction, 1 to write the value. Oh, it's 2 to write the value into memory because... Is that right? No, it's not. It's still 1 to write it into memory there. Is it 1 to decrement the stack pointer as well, maybe? Could be that. Could be that it takes a cycle to decrement the stack pointer. Let's go with that for now. Could be a bad idea doing that in there. Right, here we go. Oh. Yeah, so that works for now, but we don't know if that's going to work for everything. But again, it's a good start. So let's just keep going and do the next one. Push processor status onto the stack. Oh, okay. So this is going to be almost the same. Except let's put a weird processor status in there. Let's just put some random value in the processor status. CC, I don't know. Yeah, because that's the 0, that's the 11001100. So we want to push the, oh, that's the program counter. I want the processor status. Push the processor status onto the stack. Okay, PHP. 3 cycles, and Yeah, so this kind of comes out the same now, is that we expect this address +1 to be the, well, we expect that to be CC. Just going to do that just in case this process status has changed, and the process status shouldn't change from this anyway, so that's fine. That is all that's needed for that test. PHP can push process status onto the stack. That was one of the reasons I realized that we needed that as a byte, because we need to operate on it as a byte sometimes instead of having it as bit fields. That one is 08. Right, let's do that one. I suppose this, it gets a lot easier now, does it? Because it's push byte onto stack and it's the processor status. I think that's it. Is that going to work? Yeah, that's all it really was. So let's do the next one. Pull accumulator from stack. So this is going to take stuff off the stack and put it back into the accumulator. That's the opposite of what we did up here. So this is the opposite of PHA. So let's do it next to that one. PLA can pull. Right, so this time I'm going to zero the A register just so that we can put a value in there. I'm going to put something on the stack at FF. Just going to put something there because I know that's where we're going to be. In fact, I can force it here as the stack pointer is going to be FF. I can put a random value onto the stack there. I'm going to do PLA. So just run that, and that should pull the 42 that's on the stack. Yeah, it should pull the 42 that's on the stack and should put it into the A register. So at the end of this, I expect the A register to be 42. I expect, that's not right, I expect the, well, let's not test the status registers on this one. Let's just get this one working. This one takes 4 cycles. It's 68. We want 4 cycles for that. So that compiles and it should fail. Yep. And now we can go and implement that one. So this one, let's put it next to PHA. So we want to pop byte from stack, don't we? Pop byte from stack. I want to pop it into the A register. I think that's the only function we need for that, isn't it? Pop byte from stack. So this, instead of taking in a value, is going to return a value. I suppose we can increment the stack pointer. Is this right? Because the stack pointer will be pointing to the next thing that we want to write to. But we want to move it back to the previous part, which is that, then convert it to a word, and then read the value there. And I don't know if that's going to consume 2 cycles. Doesn't seem, I think I might have got this wrong. I suppose we can breakpoint in here and just see what it's going to do. Stack point is FF, That's going to wrap round to 0, and then I'm going to convert that to 100. That's like wrap the stack. That's not what I want it to do. Oh yeah, because the test is wrong. Because if I had just pushed a 42 onto the stack, if I had a 42 on the stack there, the stack point would be decremented to FE. So that's a better test. Otherwise, I'm wrapping the stack point around. That couldn't be right. So let's just hit that again. Where are we? I mean, I don't think it's... I mean, I can run it and just see. It doesn't pass. But let's just make sure that we know why. So we are going to, move it back up to FF and get the actual stack pointer, read the value, which is 42, and we consume 2 cycles for that, and we stick that in the A register. That seems right. I just don't think we're consuming enough cycles. So I'm just going to assume right now that this consumes 3, which we don't know if that's true, but it certainly is something. So let's do that. Right, okay, that's a pass. So I've got that working, but we need more tests for this because we need to make sure that we set the status registers. So this can pull a 0 value from the stack. So we're actually going to pull, we're actually going to put 0 there. We'll set the garbage into the A register this time, and we expect the A register to be 0, but what we do expect is that the 0 flag has been set to true. And just to make sure that it does do that, just before we start, we'll set it to false. Okay, now that test fails because we haven't written that piece of code, and there is one more test that we want as well. Can pull a negative value from the stack. So again, this case we want the negative value is false. A register's got some weirdness in it. We want a value on the stack at the point that's just got the negative flag set. So actually it doesn't matter if it's like that, it can be that, that's fine. Then we expect the A register to be that value when it's finished, and we expect the negative flag to be true. We also expect the 0 flag to be false on that 0 flag. So we might as well set that to true. I'm just setting it to the opposite of what I want it to be at the start of the test. Same with this one up here. The negative flag must be false on this one. And I'll set the negative flag to true at the start. So hopefully that's a good test for pull accumulator. 2 more good tests, and then I just implement the code that makes that work, which is load register set status for the A register. And this should just make it pass, which it does. Right, so we've got one left, and it's pull processor status from stack. This pulls the 8-bit value from the stack and puts it and just sets the processor status. Flags will take on new states determined by the value pulled. So that seems quite an easy one as well. So pull processor. Let's just copy our pull. Let's copy this one. So pull PLP can pull a value from stack into the processor status. Cool. So A register, we don't care about the A register. We've got, well, we're going to go with 42 again. So we're going to assume that we're going to pull this value off the stack. The value is PLP. We expect to take 4 cycles, and we execute that. So at the end of this, what we expect is, let's set the processor status before we start just to 0. At the end of this, we expect the processor status to be 42. That's really that's the whole test. So let's add that instruction. 28. Add the opcode, I mean, for the instruction. Right, instruction 40 not handled. That makes sense. And we are going to implement that one as well, and that's very similar. It's PLP. It pops a byte from the stack, and it just sets the program processor status to that value, which is not going to affect the A register. Now, I don't believe that's going to consume enough cycles, but it did. So we are all good. That is all of those stack operations implemented, I believe. Maybe I could just add a few more things to these before we stop. One of these things is we could probably test what we expect the stack pointer to be after these. So in the case of this one, we want to push the processor status onto the stack. We expect it to be FE on that one, because it starts at FF and then we've gone down to, is that right? Stack pointer, what's wrong with you? Does that not compile? Oh, it does. I think that still works. Yeah. So we can probably just make sure that the stack pointer got incremented as well. This one is can pull a negative value from the stack. So in this one, stack pointer should go from FE up to FF. You know, where there's nothing on the stack. That's still good. And what's this one? Can pull a 0 value from the stack. Again, this expects the stack pointer to go up to FF. It did. Can pull, again, goes up to FF. This one can push a register onto the stack. Expect the stack pointer to go to FE because we're pushing an 8-byte value. It's all passing, it's all good. Transfer, register, transfer, and the stack doesn't get affected by this one, so there's nothing to do there. But there we go, that is these stack operations implemented. How many tests did I write there? I'm not exactly sure, let's have a look. 10 tests for stack operations. So it's 10 more tests have been written, and I have got 6 more instructions or opcodes working. It takes me to 41, I think. So I'm pretty happy with that. In the next video, I will attack some more of these instructions and see how many more we can get working. But that was a really quick one, and these are getting easier and easier as I go because I've got so much code that I can lean on now. So that's great. So I'll catch you in the next one.